Okay, problem 3 says a pendulum is constructed from a thin, rigid, and uniform rod with a small sphere attached to the end opposite the pivot. Okay, thin rod, small sphere. This arrangement is a good approximation to a simple pendulum because the mass of the sphere, which is made of lead, is much greater than the mass of the rod, which is made of aluminum. Okay, the period of the pendulum is 0.76 seconds. When the sphere is removed, the pendulum is no longer a simple pendulum, but is then a physical pendulum. What is the period of the physical pendulum? What the heck? Who makes up these questions? Oh yes, that's me. Okay. Well, actually, this is not so bad. What we're going to do is remove this mass from the end. So let's call this the initial situation. Is you've got this thin rod, so the mass is negligible. And then you've got this large mass, so m, much greater than little m. And we're going to say that T initial is 0.76 seconds. So for the simple pendulum, we have this equation, simple equation from chapter 14, which is that omega, I'm going to call this initial, is equal to, I guess it's the square root of g divided by L. I'm going to call L to be the length from the pivot to the big mass at the end, capital M. And then the period is just 2 pi over omega. Okay, so fair enough. And then finally we change this system. Whoop. Add another page. So the final system, we take off that big mass at the end. So that's going to look just like the rod. And then the whole thing just sort of swings back and forth. Now, okay, I'm not going to get into the torques of all this because we didn't really do torques in chapter 12. We sort of skipped them this semester. But the idea is that this is a physical pendulum, and there is an equation for the period of or for the omega of a physical pendulum. We're going to call that omega final is equal to the square root of m times g times L divided by I. Okay, this is actually this equation, if you want to find it in the textbook, it's equation 14.52. And m is the mass of the rod, and I is the moment of inertia of the rod. Now we did moments of inertia in chapter 12, and we even looked at some table values for different shapes, and I think that for a thin rod, okay, pivoted about its end, about the end. If we look back on table, what was the table? Table 12.2. We see that I is equal to a third. M times L squared, where L is the length of that rod. Oops, I said a third, but I wrote a half. A third. Better. So we can plug that in, and we'll see that omega final is equal to square root of little m times g times L divided by 1/3. So do that again. Little m times L squared. So this L cancels with the square, the m's cancel, and you get the square root of the 3 will come to the top times g divided by L. Okay. And if you compare that back with our equation near the top of the screen for omega naught, or the original omega, this is equal to square root of 3 times it. So I guess now we can just find what the final period is. It's 2 pi over this changed omega. So it's 2 pi over square root 3 times omega naught. So this was the old period, so it's just equal to the old period divided by square root 3. And we have the old period, so it's 0.76 divided by square root 3. So I got, it's my calculator, 0.44 seconds. So just to assess that, what has happened? Well, by removing this mass from the end, you've kind of decreased the effective length of this pendulum, right? You've said that now most of the mass is a little bit closer to the pivot. So I'm just going to assess and say the effective length of the pendulum is decreased, is less. We know that the period increases with length, right? So if you shrink the length, you're going to decrease the period. So period is a bit less, not hugely less, but so that's okay.